today to talk about a 2 years journey of building a scalable event processing system at DoorDash. So first, let's talk about the use cases. At DoorDash, real-time events are an important data source to gain insight into our business and help us making data-driven decisions. Just to give you a few examples of how real-time events are used at DoorDash. First, almost all events need to be reliably transported to our data warehouse, Snowflake, or other online analytical data sources with low latency for business analysis. For example, the Dasher assignment team relies on assignment events to detect any bugs in their algorithm at near real time. And the second use case is mobile application health monitoring. Some mobile events will be integrated with our time series metric backend for monitoring and alerting so that teams can quickly identify issues in latest mobile application releases. And the third use case is sessionalization. We would like to group user events into sessions and add session-related attributes to those events so that we can better analyze user behaviors. Historically, DoorDash has had a few data pipelines that get data from our legacy monolithic web application and ingest the data into Snowflake. Each pipeline is built differently and can only process one kind of event. They often involve mixed data transports and third-party services before the data finally gets into the data warehouse. In the example that you can see on this slide, the data goes through a UDP, SQS, and then Kinesis, which is really a lot of data hops. And the result of doing that is high latency, operational headaches, and significant cost. So 2 years ago, we started to rethink this approach and decide to build a new system to replace those legacy pipelines and address the future event processing needs that we anticipated. So first, it should support heterogeneous data sources, including microservices and mobile or web applications, and be able to deliver the events to different destinations. Secondly, it should be easily accessible for data consumers to tap into streams of data and build their own processing logic. To improve data quality, we want to have end-to-end schema enforcement and schema evolution. And lastly, it should be scalable, fault tolerant, and have low operational overhead. So 2 years ago, we started the journey of creating from a real event processing system we called Iguazu. An important design choice we made is to shift the strategy from heavily relying on AWS and third-party data services to leveraging open source frameworks that can be customized and better integrated with the DoorDash infrastructure. And fast forward to today, we scaled Iguazu from processing just a few billion events to hundreds of billions of events per day with 4 nines of delivery rate. Compared to legacy pipelines we have, the end-to-end latency to Snowflake is reduced from a day to just a few minutes. So this is the architectural overview of Iguazu. As you can see, we use Apache Kafka for PubSub and decoupling the producers from consumers. And we use Apache Flink for data transformation and stream processing. The data ingestion from microservices and the mobile clients are enabled through our Iguazu Kafka proxy. For our data consumers, we provide a stream processing platform based on Flink and support both data streams and SQL APIs. After the stream processing is done, the data is sent to different destinations, including S3 for Snowflake and Data Lake, P-Node for real-time analytics, and Chronosphere for operational metrics monitoring. And in the next few slides, I'll discuss the details of producing events, stream processing, and schema enforcement. So let's first talk about producing events. And the main focus is to make event producing as easy as possible and optimize for workload of analytical data. One challenge we face here is how we can enable every DoorDash service to easily produce events to Kafka so that we can gain quick adoptions. And the solution is to leverage Confluence Kafka REST proxy. The proxy provides a central place where we can enhance and optimize event producing functionalities. It provides abstractions over Kafka with HTTP interface, eliminating the need to configure Kafka connections from all services and making event publishing much easier, especially on the mobile side. The Kafka REST proxy provides all the basic features we need out of the box. One critical feature is that it supports record batching in requests, which makes request processing efficient and scalable. And as illustrated in the diagram in this slide, you will observe that Kafka client in the proxy will also batch the requests when producing to Kafka. The end result is that you'll be able to batch requests across instances and applications, which makes the event producing to Kafka very efficient. And to improve the proxy's throughput and scalability, we also spend a significant amount of time tuning Kafka producer properties used by the proxy. What we have found out is that the default Kafka producer configuration is designed for systems requiring high consistency. For example, it will retry forever and set linger time to 0, effectively disables batching. And these settings are inefficient for non-transactional event publishing and processing, where throughput and availability are important. And therefore, we fine-tuned our Kafka topic and the proxy producer's configuration to achieve high efficiency and throughput. On the topic level, we use replication factor of 2 with one minimal in-sync replica. And compare with the typical configuration of 3 replicas, this saves the disk space and reduces the broker's CPU utilization on replication, while still providing adequate data redundancy. The producer is configured to receive acknowledgement from the broker as soon as the leader of the partition reduces the response time of the produced request. And we leverage Kafka's sticky partitioner by setting a reasonable linger time, which significantly improves batching and reduces the broker's CPU utilization. So with all these tunings, we are able to reduce the Kafka broker CPU utilization by 30 to 40%. As I mentioned above, REST proxy adds an important abstraction on top of Kafka, but it is still non-trivial to have a right client implementation to send requests to the proxy, especially in order to take advantage of the request batching. So we developed a client library to further simplify the integration with the proxy. The client library batches the events using an in-memory queue, and also takes the responsibility of serializing the events using appropriate schemas. And this reduces the workload on the proxy side. And all the work on the client side is done in a non-blocking and asynchronous fashion to ensure the client application's liveness and availability. We also introduced extensive set of metrics in the client library to help monitoring the event publishing and for us to correlate those metrics with the server-side metrics in troubleshooting. The Kafka REST proxy turns out to be relatively straightforward to build and deploy in our own Kubernetes infrastructure. We build directly from source and leverage all the CI/CD processes offered in our infrastructure. And based on CPU utilization, Kubernetes horizontal pod autoscaling is enabled on the service. This significantly reduces our operational overhead and saves cost. And the diagram in this slide shows autoscaling effect of the proxy. So now that I have covered events producing, let's focus on what we have done to facilitate event consuming. As mentioned in the beginning, one important objective for Iguazu is to create a platform for easy data processing. Apache Flink's layered API architecture fits perfectly with this objective. We chose Apache Flink also because of its low latency processing, native support of processing based on event time, fault tolerance, and out-of-box integration with a wide range of sources and sinks, including Kafka, Redis, Elasticsearch, and S3. So one important feature of Flink is that it supports different levels of abstractions. So in this diagram, you can see that at bottom, for engineers who want to have a tight control over process logic and be able to highly customize the code, they can choose the process function layer, which gives them the precise control over how they can handle events, state, and time. And next level up, Flink offers data stream APIs with built-in high-level functions to support different aggregations and different windowing. So the engineers can create a typical stream processing solution with just a few lines of code. And on top, we have SQL and table APIs, which offer casual data users the opportunity to write Flink applications in a declarative way using SQL instead of code. And to help people at DoorDash leverage Flink, we have created a stream processing platform on top of Flink. Our platform provides a base Flink Docker image with all the necessary configurations that are well integrated with the rest of DoorDash infrastructure. Flink's high availability setup and the Flink internal metrics will be available out of the box. And for better failure isolation and the ability to scale independently, each Flink job is deployed in standalone mode as a separate Kubernetes service. And data stream APIs and the Flink SQL are the two abstractions that we support on this platform. So here's a diagram of the build and deployment model of Flink applications in DoorDash. So take applications developed with Flink code as an example. You first start the application development by cloning our Flink application template and then add your own code. And then in build process, a Docker image will be created, which combines the application jar file with our internal Flink-based Docker image. When it's ready for deployment, you will create Terraform service templates, which include configurations for both the application and the resources. The deployment process will take both the service templates and the application Docker image, translate those into a Helm chart, and deploy the application as a standalone Flink job. And to support SQL-based applications, we created a framework called Riviera, where all the necessary processing logic and wiring are captured in the YAML file, which is simple enough for everyone to read or author. The YAML file captures a lot of high-level abstractions, for example, connecting to Kafka sources and different sinks. And the processing logic is expressed as a SQL statement. And currently, Riviera's primary use cases are real-time feature engineering and real-time monitoring of mobile application metrics. So if you are interested to know more details, please check out our Riviera tech blog. And here's a concrete example of how Flink SQL is used in Riviera to derive stored order count for each restaurant in the last 20 minutes, with the results refreshed every 20 seconds. In this example, I'm showing the whole YAML file, which is the only thing you will need to author to create the Flink application. In this YAML file, you need to specify the source, sink, and the schema used in the application. And one thing to note here is that all the source and sink applications are abstracted out, so you don't need to be concerned about infrastructure dependencies. And the processing logic is expressed as a SQL query. The hop window here indicates that you want to process the data that are received in the last 20 minutes and refresh the results every 20 seconds. So in the above two sections, we covered events producing and consuming in Iguazu. However, without a unified event format, it's still difficult for producers and consumers to understand each other. So in the next section, we will discuss the event format and schemas, which serve as a protocol between producers and consumers. So from the very beginning, we define a unified format for events produced and processed in Iguazu. The unified event format greatly reduced the barrier in consuming events and reduced the frictions between the event producers and consumers. To start with, all events have a standard envelope and payload. The event payload contains the actual content of the event, which is usually encoded with a schema. The envelope contains a context of the event. For example, event creation time, metadata, including encoding method, and references to schema. The envelope also includes non-schematized JSON blob called customer attribute. This JSON section in the envelope gives user a choice where they can store certain data and evolve them freely without going through the formal schema evolution. And to facilitate event publishing and consuming with schema enforcements, we created serialization and deserialization libraries for both event producers and consumers to interact with this standard event format. In Kafka, the event envelope is stored as a Kafka record header, and the schema encoded payload is stored as the record value. Our serialization library takes the responsibility of converting back and forth between event API and the properly encoded Kafka records so that the applications can focus on their main logic. We heavily leveraged Confluent schema registry for generic data processing. Schema ID is embedded in the event payload, so the downstream consumers can look it up from schema registry without relying on the object classes on the runtime class tab. And both protobuf and Avro schemas are supported in our serialization library and schema registry. We support a protobuf schema because almost all of our microservices are based on gRPC and protobuf, supported by a central protobuf Git repository. So to enforce this single source of truth, avoid duplicate schema definition, and to ensure the smooth adoption of Iguazu, we decided to use protobuf as the primary schema type. But on the other hand, the Avro schema is still better supported than protobuf in most of the data frameworks. So when necessary, our serialization library takes the responsibility of seamlessly converting the protobuf message to Avro format and vice versa. One decision we have to make is when we should allow schema update happen. And there are two choices, either build time or producer's runtime. It's usually tempting to let producers freely update the schema at the time of event publishing. However, it will lead to spikes of schema update request volume at certain times, causing scalability issues for the schema registry. And it may lead to data loss because any incompatible schema change will fail the schema update and cause runtime failures in event publishing. So instead, we concluded that it would be ideal to register and update the schema at build time to reduce the update API call volume to schema registry and to catch incompatible schema changes early in the development cycle. But one challenge we faced is how we can centrally automate the schema update at build time. And the solution we created is to leverage the fact that all of our protobuf schemas are managed in a single repository and integrate the schema registry update as part of the CI/CD process. When the protobuf definition is updated in the pull request, the CI process will validate the change with schema registry, and it will fail if the change is incompatible. After CI passes and the pull request is merged, the CD process will actually register or update the schema. The CI/CD automation not only eliminates the overhead of manual schema registration, but also guarantees and the
Seems to have a audio problem. Alan, we couldn't hear you anymore.
To ensure its scalability. So far, we have talked about event producing, consuming, and event format. And in this slide, I will give some details on our data warehouse integration. As I mentioned in the beginning of the talk, data warehouse integration is one of the key goals of Iguazu. Snowflake is our main data warehouse solution. We expect events to be delivered to Snowflake with strong consistency and low latency. The data warehouse integration in Iguazu is implemented as a two-step process. In the first stage, data is consumed by a Flink application from Kafka and uploaded to S3 in the Parquet file format. And these steps helps to decouple the ingest process from Snowflake itself. So any Snowflake-related failures will not impact the stream processing. Also provides a backfill mechanism from S3, given Kafka's limited retention. And finally, having the Parquet files on S3 enables data lake integrations as Parquet files can be converted to a desired table format. And at the second stage, data is copied from S3 to Snowflake table via a Snowpipe, which is Snowflake's solution to load data at near real time. Triggered by SQS messages, Snowpipe enables loading data from S3 files as soon as they are available. Snowpipe also allows simple data transformation during the copy process. And given that Snowpipe is declarative and easy to use, it is a good alternative compared to doing data transformation in stream processing. And one important note here is that each event has its own stream processing application for S3 upload and its own Snowpipe. And as a result, we can scale pipelines for each event individually and isolate failures. So far, we covered the end-to-end data flows from clients to the data warehouse. In this section, I will discuss the operational aspect of Iguazu and see how we are making it self-serve to reduce the operational overburdens. As mentioned before, to achieve failure isolation, each event in Iguazu has its own pipeline from Flink job to Snowpipe. However, it requires more setup work and makes the operation a challenge. And this diagram shows the complex steps required to onboard a new event, including creating Kafka topic, schema registration, creation of a Flink stream processing job, and creating the Snowflake objects. There's something pop up on my screen, and I have to deal with it. Give me 1 second. Okay. I'm fine now. All right. So we really want to automate all these manual steps to improve operational efficiency. But one challenge we faced is how we can accomplish it under the infrastructure as code principle, where most of operations, including creating Kafka topic, setting up service configurations, involves pull requests to different Terraform repositories and requires code review. To solve this issue, we worked with our infrastructure team to set up the right pull approval process and automate created where we can programmatically create and merge pull requests from a service which acts as a controller. We also leveraged the Cadence workflow engine and implemented the process as a reliable workflow. This whole automation reduced the event onboarding time from days to minutes. And by combining automation with infrastructure as code, we get the best of both, where manual steps are removed, but we still get versioning, all necessary code reviews, and consistent state between our code and the infrastructure. And to make it one step closer to self-serve, we created UIs for users to explore schema and onboard an event from there. Users can search for a schema using regex, pick the right schema for the event, and then start the workflow to create necessary resources and services, and have the opportunity to customize a Snowflake table and Snowpipe. This screenshot shows the schema exploration UI, where users can search and drill down to different schemas, subjects, and versions. And then this screenshot shows the UI where we can manage the Snowflake table schema and Snowpipe. And most importantly, we created a service called Minions that does the orchestration of the workflow and have it integrated with Slack so that we will get notifications on each step it carries out. So on this screen, you can see about 17 actions it has taken, including all the pull requests, launching a Flink job, and creating Snowflake objects. So in this talk, I discussed the design and architecture of Iguazu and covered event producing and processing, event format, and automation. And here are some closing thoughts and takeaways. First, I find it important to create the event processing system with a platform mindset. Ad hoc solutions are not only inefficient, but also difficult to scale and operate. And secondly, picking the right framework and creating the right building blocks is crucial to ensure success. Researching and leveraging the sweet spot of those frameworks dramatically reduces the time needed to develop and operate this large-scale event processing system. And finally, to make the system user-friendly and easy to adopt requires the right abstractions. With the declarative SQL approach, seamless serialization support, And the high-level user onboarding UI, we strive to simplify event processing so that our users can focus on their own business logic and not our implementation details. So that's all I have today. And if you want to know more details, please check out our DoorDash tech blogs. And thanks again for attending this talk.
Thank you, Alan, for the excellent talk. For the audience, if you have questions, you can post on the chat. Let me kick up the question with my own. So can you elaborate a little bit more on the architecture choice at the beginning when you explain that, say, hey, the existing the legacy systems is using AWS services, and these services in some senses are kind of similar, have the counterpart of what you choose eventually. You have a Kinesis, and you have a Kafka, you have other streaming processing, and you Flink, and then they have something similar. So what is the main things, maybe a couple of main things technically that you decided to say, hey, the AWS services doesn't serve our needs? And also on the business side, probably is assume that the cost is another factor.
Yeah, that's a good question. So maybe you can go back to that. I'll go back to that slide. Yeah, so this is the one of our legacy pipeline, right? I think the question is around this pipeline, what's changed in our new pipeline. So in this pipeline, you can see the data goes through UDP server, SQS, and then Kinesis. But in the new pipeline, all those three components are just replaced by Kafka with one single pops up service. And as I mentioned, there's really no need to go through so many steps in the pipeline. I think the UDP server is perhaps a poor, or maybe that's one of design choice to decouple the monolithic web app from this event publishing logic, because I don't know why they choose to do that. Probably it's not a very good choice. And then the SQS and the Kinesis, they are basically, they have the similar functionalities. And adding those two kind of queuing service all together in the mix, it actually becomes a headache, because I remember when we are operating this, when there's a delay or there's some back pressure happening, we have to find out exactly where's the bottleneck. Is it Kinesis the bottleneck, or is the SQS the bottleneck? And there are so many metrics to look over to pinpoint the issue. So yeah, I think that's this is really not very good design. And that design was already there before I came on board to DoorDash.
Thank you, Alan. So let me read us a few questions from the user. Let's see. The first question is basically talking about the protobuf to Avro conversions. Is this something you custom developed or something out of the shelf?
Yeah, this is something out of the shelf. It's a part of the Avro library. There's a protobuf, I think it's called protobuf, Avro protobuf. Yeah, there's a sub module in the Avro library that you can leverage.
I see. And then the other user is asking, what's the typical end-to-end latency in your pipeline for the new one?
So, yeah, for the new one, if we just talk about latency of data getting into Kafka, it's just on the sub-seconds level. But the end-to-end from the client to the data warehouse is usually within 1 minute, 1 or 2 minutes. But sometimes it can go up to maybe a few more minutes, keeping in mind that sometimes we have to redeploy the job, the stream processing job, and that actually causes some delays, but that happens very rarely.
Okay, question about the schema registry. Is that a custom tools or something off the shelf like a Confluence or AWS Glue registry?
Yeah, that's the Confluence schema registry.
Okay. Okay, so let's see. What are some of the challenges facing using Flink and some of the best practices?
The challenge of using Flink is that typically there's a learning curve for, let's say, a backend engineer or a product engineer if they want to develop a stream processing application, and that kind of logic is quite different from the logic you would see in the user-facing service. So the concept of, let's say, checkpoint, the concept of a job, and the coordination between the job manager and task manager, and the failure recovery that's provided by Flink. If you want to fully leverage all of those, you really need to dig into the Flink documentation and find some good examples to learn from that. So that's why I think it is best to provide different level of abstractions for people who can write code, who wants to write code, to fully explore the different features of Flink, and have customized processing logic. Yeah, definitely go use data stream APIs. But if you provide also the SQL abstraction as a platform, that will open up the use case of Flink to more casual data users like data analysts or some data scientists.
Sure. The next question is, can you speak more of the tooling using protobuf and ever schema conversion? I guess you already answered this one. Are there any public tools to help to make this easier? We have a similar problem. Most engineers using protobuf, but some events are in Avro and others and all other formats. Harmonizing to protobuf under the hood sounds really attractive.
Yeah, I think this basically goes back to the protobuf to Avro conversion, and again, I think I would say 95% of issues can be resolved using the built-in library in Avro that can convert from protobuf to Avro.
Okay, the next question is about the Flink. It's basically Flink, the state management. Say, it says my biggest challenge working with Flink were state management for stateful event processing. Do jobs tend to avoid maintaining state? Or if they do have state, do you have issues with the latency with the Flink jobs are starting up and restoring states?
Yeah, so I would say maybe 60% of our jobs are either stateless or have very little state, but there are about 40% of jobs that do have state, and I think there are a few. So we actually have explored a few solutions for stateful applications. I think the one biggest thing that we find out is that you want to leverage you want to choose the proper state backend. And the state backend is very fundamental to help manage the state and provide necessary fault tolerance. And I think in one of those, our big state, the huge state jobs, we use the RocksDB backend. And there are some, I think there are some learning curves actually with the RocksDB, and there's some tuning needed. But in general, I feel RocksDB provides a very good performance in stateful applications because it's the only state backend that supports incremental checkpointing, which really reduced the latency in checkpointing and reduced the size of the state. So that's one thing that I find out.
So, okay, the next question. How was the application tested and make sure one record flow from beginning to the end?
Yeah, that's so right now, that's a very good question. Right now, we are primarily using count to ensure that we have at least once delivery. So we are not at the level where we can trace each individual record. So yeah, the primary tool is to gather the metrics at the client side and gather the metrics at each step of the processing and compare those metrics, make sure that there's no metric loss, there's no data loss at each state.
Okay.
And I think in general, once the data gets into Kafka, Flink provides very good delivery guarantees. You can choose either at least once or exactly once. So, for example, for the file upload to S3, we use the Flink's streaming file sync, and if I think it is a very well written, and we test that, and we find out that it actually provides exactly once guarantee. Once you I think once you config the sync to act together with the checkpoint.
So the same person also asked that when you say framework should be created, how do you design a framework? Please elaborate. It's like a pretty general question.
Yeah, I think as I mentioned before, keeping your customers in mind, creating different kind of abstractions, make sure that whenever you see opportunities, try to put all the common functionalities in your platform, and so that you can reduce the necessary workload from other applications, and really just to make sure that that as a platform, you will capture all the necessary interactions with the infrastructure, and then let the application to worry only about its business logic, but not at the infrastructure level.
So the next question is about choosing Spark versus Flink, and see what's your thoughts on that.
We actually, I think Spark and Flink has its own use cases. We didn't really go into a lot with evaluating Spark for our team or for that platform. But I think the reason that we chose Flink is its low latency processing, and it is able to support event processing, basically support processing on the event timestamp. I think for Spark, I think maybe a few years back, it's using micro batching. So I think maybe their use case a little bit limited to streaming that does not require, let's say, sub-seconds latency, but more like minutes kind of latency. Yeah, other than that, I really don't have a comment on
that. Okay, another challenge, this is from the other user. Another challenge that I'm seeing with the Flink is tuning the distribution of the memory between the JVMs and other components like a RockDB backend, especially when you push the Flink job onto extreme powerful systems with a high amount of hundreds of gigabytes of RAM. How much time and effort would you say was put into that?
Yeah, I remember when we started tuning our first very big stateful processing job, we spent about 2 weeks in tuning the RocksDB, and actually we run into issues of certain memory leaks or maybe and also the the obsolete files on the EBS, which takes up all the disk space, and we have to find out a few solutions to deal with all that kinds of things. So yeah, it's about 2 weeks of time, but in general, we followed the documentation that we have found on the official Flink website, and we were able to search for all kinds of solutions and apply them in our work. So after I would say maybe 1 to 2 weeks of tuning, our jobs runs in good state right now.
Good. Get 2 more questions, and I think that we pretty much are out of time. One is how do you monitoring the state of a data lake and data warehouse in Snowflake?
Yeah, that I don't. Yeah, I'm not sure what the question is. Snowflake itself probably have a very good state management, but I'm not really. I don't have details on that.
Okay. And it's totally understandable. And then the other question is talking about the metrics backend and the time series DB used.
The metric that's the Chronosphere. So we use Chronosphere for our metric backend.
Okay, last question. So Bradley was asking. So you mentioned EBS based RockDB backend. Have you spent any time using SSD-based EC2 instance types to see if they improve the performance?
No, we haven't done that. The reason is that our underlying infrastructure only supports EBS as the persistent volume. So basically we use EBS for that. But we haven't found any issues for the disk performance of EBS.
Great, thank you. That's pretty much. Oh, somebody asked another question. Sorry. Okay. Well, last one. So no more questions. Okay. Are these any scenarios of events loss, especially on the consumer side? And if so, how do you manage for making up for that?
So most of the event loss does not happen on the consumer side. As I mentioned, once your data gets into Kafka, Flink provides Kafka provides very durable storage for the data, and the Flink itself provides at least or exactly once delivery guarantee. Most of the data loss happens before data gets into Kafka and happens on the client side. So sometimes they have their own bugs in the client application. Sometimes they didn't allocate enough resources to be able to produce that large amount of data. So that's the majority of data loss happens, not on the consumer side.
Okay, that's all the questions. Thank you, Alan, for the great talk and all the answers. So thanks everyone for the great questions. Thank you so much, and I'll see you next time. Okay, bye-bye.
Thank you. Thanks everyone for attending. Bye.